Hello, everyone. I am Siddarth Asokan, a research engineer at Microsoft Research India, and I completed my PhD under Professor Chandrasekhar Seelamantula at the Indian Institute of Science, Bangalore. Firstly, I would like to thank the Indian Unit of Pattern Recognition and AI Committee for the Doctoral Dissertation Award and ICVGIP for giving me an opportunity to present my work here. Today, I'll be giving a brief overview of my PhD dissertation, which is on the optimality of generative adversarial networks viewed from a variational perspective. To provide a bit of context, my thesis was on generative adversarial networks, or GANs, which comprise a two-player game between a generator, which transforms Gaussian noise into realistic images, and a discriminator that takes in these generated samples and those from the dataset and learns to classify them as real or fake. The optimal solution is to find the best generator, one that can completely fool the discriminator. My research primarily focused on deriving the optimality criteria for the various components in the GAN by leveraging fundamental results from classical mechanics, electrostatics, signal processing, functional calculus, and differential equation theory, just to name a few sources. To give a flavor of this thesis, in the first part, considering various GAN discriminators with popular gradient-based regularizers, we showed that the optimal function that the discriminator network is trying to model is the solution to a Poisson partial differential equation, or PDE. And sometimes this can be generalized to a PDE involving the iterated Laplacian operator as well. These results were useful to us because we could then show that the optimal discriminator could be implemented in closed form without the need for any additional training of the parameters. And although a bit challenging to scale, when we applied this solution to the latent space matching for image generation, we outperformed the baseline significantly. Essentially, these would be 1 to 2 layer hand-designed discriminator networks with weights obtained by solving the PDE with no need for backpropagation. Along another axis, we also explored the optimal input to the GANs, going beyond standard noise distributions like the Gaussian. We were able to show that if chosen correctly, any input dataset could be given to a GAN, like cars or planes, and transformed to any output dataset, like faces. We derived novel metrics to help in choosing which input distribution can best show gains given an output dataset we want to learn. This approach led to 5x improvements in training time while achieving comparable to state-of-the-art performance on underrepresented datasets and superior image interpolation performance. In the latter parts of the thesis, we also show that a majority of these results that were derived could be ported to the now popular score-based diffusion model setting, wherein the optimal discriminator could be used for guidance in Langevin sampling. This discriminator-guided sampling can improve the quality of the generated images by reducing defects and artifacts with no additional training overhead. To summarize, I've touched upon a very small set of the results we derived. So be sure to check out these papers to learn a lot more about my work if you found it interesting. And once again, thank you to IUPRAI and ICVGIP for the award and giving me this opportunity to present my work.